Okay, so we are live now. Let me share my screen. So can you confirm that you can see, anyone can confirm that you can see the screen?
Yes, sir.
Okay, thank you. So today is our last class for classical cryptography, and you will see that we will do cryptanalysis of two ciphers. One is substitution cipher, and the other one is Wagner cipher. Uh, the substitution cipher cryptanalysis is a little bit clumsy, but it works actually. So I will give you sort of an outline so that you understand how things are working. But of course, you need to do a lot more practice, or maybe so it's more context based basically, rather than of course it involves frequency analysis of alphabets, but also a context based things are there. So sometime it is a little bit clumsy, but anyway, so let me but it works actually. That is the beauty of this. Okay, so so today, as I mentioned, so we will be finishing the classical cryptography things. Uh, we talked about shift cipher, substitution cipher. So remember substitution cipher. We have plain text and ciphertext over Z26, and possible permutations are nothing but the key which can permute. So basically, just substitute the alphabets. So we need to somehow break this system. Then we will also talk about Wagner cipher, and here it's a beautiful one. I mean, it's a well-established method. So and then briefly we'll talk about Hill cipher. Okay, so let me go back. So I think in the first one, so we will be looking at known ciphertext attack. Basically ciphertext is given to you. So in case of substitution cipher and Wagner cipher, uh, we will assume that ciphertext is given to us, and then we will try to decrypt. Okay, whereas for Hill cipher, we will assume that it is ciphertext is also given and plain text is also given, right? So then see how to decode that. Anyway, so this Baker and Piper table is very, very important. The statistical properties of English, as I mentioned, that if you look at any running text of English, newspaper, magazine, or anywhere, this is how the probability distribution of alphabets will appear. Okay, E will appear with probability 0.120, and then we have T, A, O, I, N, S, H, R, each having probability between 0.06 and 0.09. Of course, T will appear more, and then after that A, and then O, and so on. So there are 5 groups which you can distribute in terms of probability. This table is very, very important, so I will refer frequently this table 2.1 I will call it. Okay, or Baker and Piper table. Also, these diagrams and trigrams are also very, very important, and they help you in deciphering the ciphertext. So in case of uh, shift cipher, you saw that. In case of affine cipher, you saw how to use the other the statistical properties of English, but these diagrams and diagrams are very useful for substitution cipher. So let us see how. Affine cipher, we saw how to do it. Ciphertext was given, and then we figure it out by solving a system of equations and checking whether it is legal or illegal key. Once we found legal key, we were able to decrypt it. Okay, so now we are ready to look at substitution cipher. Okay, so if you look at this cipher text given here, starting from Y, so let me, yeah, starting from Y here and ending at R, right? So if you look at how many, you can count how many characters are there, and then in terms of frequency, what is the frequency? You can see that which one is occurring more often here. You see Z is 20 times, right? So number of occurrence of Z is 20 more often than any other anything else. Okay, so now if you go to the Piper table, the Baker and Piper table of statistical properties of English, we know that E occurs most often, right, in the text. That means we infer that dkz of dk of z is E. This is our first guess. Okay, so watch it carefully. So if few things doesn't make sense, that's okay, so maybe you can go over it again and again, because you need to refer to these cipher text again and again to analyze what is happening. So just pay attention. Okay, so now remaining cipher text characters are C, D, F, J, M, R, and Y. They occurs more than 10 times. If you observe in this table, more than 10 times, these are the remaining cipher text characters that occur more than 10 times. So we might expect that these, these are encryptions of a subset of, again, I am comparing with, you see, this table. So they will be subset of this actually, So E I have already matched. Now we look at TAOINSHR, okay, because they are occurring more often here. So this is how we begin. So we will see that these characters, these are encryptions of a subset of T, T, yes, A, O, I, N, S, H, and R. Of course, you know, we expect that these are the encryptions, but in which one is what, that we don't know right now. But these things should correspond something here, or at least a subset, right? Because they are occurring more than 10 times, and these this is, I will call it as a, so second group. This is your second group in the English statistical properties of English, Piper table, Okay, so now we need to look at, in this ciphertext, diagrams of the form which are ending with Z or which are beginning with Z. Something like this I have to look at. For example, you see ZR. ZR is what? One of the diagram, right? ZR ending with R, beginning with Z, actually this is, right? So similarly, we do look at this and try to analyze. So normally we can write a computer program for doing all these things. I'm just showing you, by hand. But of course, you need to look at carefully the whole ciphertext and see which one is what. So right now we have guessed only one thing, which is that dk of Z is equal to E. Okay, so this we need to keep in mind, and that these things are basically encryptions of subset of the second group here. Okay, now we look at the diagram, which is beginning or ending with Z. So I can write it down by noting, by looking at the ciphertext, that DZ and ZW, they appear 4 times each. So you can actually, just check it here. I cannot, of course, it will be difficult for me to look at everything here. For example, DZ is here, and then it will appear somewhere else also, right? DZ is here. You can see that one DZ is here, another DZ is here, right? And you can see there 1 minute. Okay, so like that, I'm just counting. Another DZ is here. You see, for example, right? So like that, I'm counting DZ and ZW 4 times each, NZ and ZU 3 times each. I'm just looking at diagrams. Then we have RZ, HZ, XZ, FZ, ZR, ZV, ZC, ZD, and ZZ twice each. So I'm just looking at the ciphertext and trying to analyze the diagrams, right? Now I can guess certain things about encryption. Since ZW occurs 4 times and WZ not at all. You can see that WZ is not there anywhere, right? And also we know that W occurs less often than any other character. We guess the decay of W is T. This is our second guess. Okay, based on again the Pfeiffer table, right? So this is our second guess. Next, I think I need a little bit more space here. Okay, so this is our second guess. Next, DZ occurs 4 times and ZD twice. Okay, we would think that decay of D is one of them, RST. I mean, only we have this much information, not more than that. Later on, we will exactly see that RK of D is actually S, in the analysis. Okay, this implies that with the assumptions that dk of Z is equal to E and dk of W is equal to D, we just did these assumptions like this one here and this one here, right? Keeping these assumptions in mind, we look at the ciphertext again and notice that ZRW occurring near the beginning. Okay, I think you can look at it. ZRW is here. Okay. So near the beginning, and RW occurs again later on. Okay, since R occurs frequently and ND is a common diagram, again from the diagram table, we know that ND is a common diagram. We might try that DKR is equal to N. Okay, that's our another guess. So after these 3 guesses, like this one, and this one, we can look at the ciphertext. This is like this, you see. So we have decoded these many things actually, So only after 3 decoding, our ciphertext. So this is our plain text guesses, that we have right now. Okay. So now our next step will be actually, since NZ is a common diagram, okay, we again try the dk of n is equal to h. This is our another guess. And of course, NZ is a common diagram and Zn is not. So we try the dk of n is equal to h. Okay. Okay, and also, and segment of plain text of the plain text NE dash NDHE suggests that dk of C is A. So with these guesses, actually, it becomes something like this. Okay. So this is our initial thing. Next, we might consider capital M. Okay. Capital M is the second most common ciphertext character, capital M. So if you look at the table here, capital M is the second one. This is 20, capital M is 16. So this is the second most, okay, common character in the ciphertext. Okay, so now the ciphertext segment RNM. Okay, this encode for NH dash, right? This means that this suggests that H begins with begins a word. So M is probably a vowel. So our guess is that M is probably a vowel. Okay. Now A and E are already taken. A and E are already taken. So we expect the dk of M is either I or O. Okay. Now again, since AI is much more likely diagram than AO, much more likely diagram than AO. Okay. So that means we can try dk of M actually is equal to I first. And once we have this, you see, so M corresponds to I, our text looks like this. Now we try encryption of O. Okay. So O is a common plain text character. And the corresponding ciphertext character is D, F, J, Y. Now Y seems to be most likely. Otherwise, we get long strings of vowels, from CFM or CJM. We'll get long string of vowels, right? So we suppose that dk of Y is nothing but O. Now, the three most frequent remaining character ciphertext are DFJ now. DFJ. So we conjecture in some order they could encrypt RST corresponding, one of them, of course, in some order, which in some order. Okay. So now two occurrence of the trigram NMD suggest that dk of D is equal to S, giving the trigram his in the plain text. Okay, his in the plain text. So, okay, this is consistent with the DKD belongs to RST. Now, again, by looking at the segment H and CMF, and by knowing a couple of the characters, this could be encryption for chair. Okay. So this implies that we have that dk of F is equal to R and dk of H is equal to C. Just guessing, this looks like as a chair, right? So that means by once we observe these two, we know the rest, the last one, dk of J is equal to T. Okay, and so we have something like this. Now, more or less, the rest of things we try to guess from the context. Okay, so what is here? This looks like friend, right? F, so Q should be F, and so on, right? By guessing, we from the context we guess that our friend from Paris examined is empty. This is U, this is F, and so on. By guessing like this, we arrive at this decrypted text. So this is, as I mentioned, this is more or less a clumsy process, but but it works. So for each ciphertext, it will be different. So you need to observe diagrams in the ciphertext. So normally you cannot, for a small ciphertext, you can do it by hand, but for a longer one, of course, you can write a computer program. So maybe a MATLAB script or MAPL script or Mathematica. So I think I will give you some MATLAB scripts to run. Okay. So that's all about this cipher. Now I think we can look at Wagner cipher. This is really interesting cipher, as you know. Okay. So this involves decryption. So again, we are assuming that ciphertext is given to us, and we need to analyze, get the plain text from this. As you know that Wagner cipher, there is key K1, K2, KM, K1, K2, KM, like that it goes, right? So this M has to be, if you know M, then it will be easy for you to guess the plain text, right? So first you need to find out M. So it is actually 3-step process. So step 1, find M. Step 2, find key. Then step 3, find plain text. Now there are two methods to find M. One is Kasaki test, which was discovered also earlier by Charles Babbage. Okay, so you guess by computing certain distances, and the second thing is that there is a method by William Friedman, uh, index of coincidence. You compute certain probabilities to confirm your guess that what is the value of M. Once you find M, then there is a way to find key. Okay, there is a systematic way to find key. Once you find key, then you can guess the plain text. Okay, so this is so there are two methods here to find M. One is for guess, another one is confirm, and then you find a key, and then you find the plain text. So here is a ciphertext given to you. Okay, now Whenever we are getting a cipher text from Wigner cipher, one thing that was observed by some of the people like Kasiki or Charles Babbage, right? There is some distance between the common text. So let me write down that observation first here. And this is a pretty useful observation, that two identical segments of plain text will be encrypted to the same cipher text. So we are assuming that there are two identical segments of plain text, right? Say for example THE, right? THE is at one place, THE is another place in the ciphertext, right? In the plain text. So they will encrypt to the same ciphertext whenever their occurrence in the plain text is delta position apart. Where delta is a number which is multiple of m. Okay, so this is something, because you see why this is happening, because we are using same key after each. So first we are using k1 k2 km, then we are using again k1 k2 km, right? So this m is important thing. Conversely, we have something similar. If you observe two identical segments of ciphertext, each of length at least 3, okay, then there is a good chance that they correspond to identical segments of plain text. That they corresponds to identical segment of plain text. So this is a beautiful observation. So if there are two identical segments of plain text, they will encrypt to the same ciphertext whenever their occurrence in the plain text is delta position apart. Okay, uh, delta is multiple of m. Okay, so this is something important. And conversely, if there are two identical segments of ciphertext, length at least 3, for both of the segments, then there is a good chance that they correspond to the identical segment of plain text. So now Kasaki devised, or we can call it Kasaki Babbage test or Babbage Kasaki test. So I'm just mentioning that, which is useful to guess the initial value of m, which is okay. So here is a test. Kasaki Babbage test. Okay. So what we do, search the ciphertext for pairs of identical segments of length at least 3, okay, and record distance between the starting positions. We'll just do it actually of the two segments. Okay. If we obtain several such distances, suppose we get delta 1, delta 2, and so on, then we would conjecture that m will divide all of delta i's. Okay. This implies that m divides GCD over I of delta I. Okay. So this is a important thing to remember. We will see actually in this example of ciphertext, we will compute. In fact, we will see that ciphertext CHR here, CHR, okay, is at position 1, then again position 166, starting position. Okay, it will again appear to C66 somewhere. Okay. So I just mentioned it is 166, 236, 276, and 286. We can find this is there is one another CHR here, right? So you need to be an expert, right, to find out these. So you can write a small computer program to find out, the text which is at certain distance. Okay. Another one is here. You see, another one is here. If you carefully look at this plain text, you can find out CHR. Right. So I think I leave it as a new exercise for you to really do this calculation. Anyway, so now actually now I think I should mention. So I told you about this test. Okay, the Kasaki-Babbage test. How to actually find out m. This is a guessing m, right? If you find out the ciphertext with a pair of identical sequence of lengths greater than at least 3, record the distances, and then take the m divides all of delta is, then guess m, which is GCD of in fact all the delta is, right? So you can actually find it out. So that is one thing. Now look at the second method.
क्या बना है?
William Redman method. This was given in 1920. Okay. So here we define what is known as, I think I need some more space here. Okay. Okay. So in this, we need index. We define what is known as index of coincidence. Okay. So suppose, so this, suppose x is equal to x1, x2, xn is n alphabet character. So all these are alphabet characters. N characters are there. So index of coincidence of x, we call it as IC of x, is defined as probability that two random elements of x are identical. This is very, a simple thing to observe, that if you are picking up two random things, because we are actually going to look at two, ciphertext which are same, or plain or plain text which are same, right? So this is something we can talk about probabilities. Probability that two random elements of X are identical. Okay. So now we'll do a little bit more probabilities. Suppose okay, frequencies of A, B, C, Z in X are F0, F1, F25, right? There are 26 total respectively. Now I can actually compute this ICX. Two elements of X.
इसके साथ कुछ पीने का ना अभी से नहीं
Two elements of X can be chosen in n choose two ways. Okay. So because two elements of X can be chosen in n choose two ways, right? This is very common from discrete math, right? And for each I, 0 less than equal to I less than equal to 25, there are Fi choose two, right? Ways of choosing both the elements to be I, right? This is also true. Two elements of S can be chosen in n choose two ways, and for each I there are Fi choose two, because Fi is frequency, right? Ways of choosing both elements to be I, right? So in this case, IC of X is nothing but summation Fi choose two, I is equal to 0 to 25 divided by n choose two. Okay. So this is, if you want, you can compute it here. Fi minus 1 divided by 2. 2 is cancelled actually. Summation n times n minus 1. I is equal to 0 to 25. Okay. So we can compute index of coincidence like this. Now actually, there are important things. If you look at English, running English text, so we can compute index of coincidence there as well, So let me do that actually for you. And that is a very strong clue for us to determine, the value of M. So here is the result. If X is a string of English language text, if the expected probability of occurrence of letters, if the expected probability of occurrence of the letters A, B, and up to Z in the Piper table, right, is P0, P1. These are the probabilities, P25 respectively. Then IC of X actually turns out to be summation Pi square. Which is actually, because if you put the values of Pi, this turns out to be 0.065. Why this is summation Pi square? Because probability that two random elements both are A is P naught square, P naught for each. Probability that two random elements both are B is P1 square, and so on, right? So this is how we compute. Now, so this is for the plain text. Okay, this is an important result. Now, if X is a ciphertext, then what happens? If X is a ciphertext, obtained using monoalphabetic cipher, monoalphabetic cipher. Then individual probabilities will be permuted, right? I mean, these individual probabilities will be permuted because now characters are moving, okay? But the overall quantity, the summation p square will remain unchanged, right? Summation p square will be unchanged. So there is no change much, okay? Now, now there is an interesting thing. What we are going to do now, basically, in order to guess m, I am actually suppose I think this is 1 minute. I need more space here. Suppose start with a ciphertext. Now I think let us do some ciphertext analysis. Suppose start with a ciphertext string y is equal to y1, y2, yn. Now what I do? This is constructed using Wegener cipher, ciphertext. Okay. Define m substrings. Now we define m substrings of y as y1 bar, y2 bar, ym bar. So these are some bold letters you can say. So y1 is y1, ym plus 1, y2m plus 1. Okay, this is y1, y2 is equal to another substring y2, ym plus 2, y2m plus 2, and so on. Then we have ym is equal to ym, y2m, y3m, and so on. So this is m rows and n by m columns. Okay. So rows are substrings yi. But now there are two cases that may happen. If m is a keyword length, if m is the actual length, okay, then IC of yi is equivalent to 0.065, which we computed, right, for the ciphertext. Okay, if m is a keyword. If it is not, if m is not a keyword length, then IC of y IC is actually equivalent to, it's totally random actually in that case. 26 divided by 21 by 26 square is equal to 038, something like that. It's very random. Okay, so basically 0.0065 0.065, sorry, 0.065 and 0.038. These are the two probabilities in which, so they are fairly distance apart. So actually by looking at this index of coincidence, we can make sure that what is the length. So let me do the example. Now we look at this example in front of us. In this, as I mentioned, if you look at the CHR, it is at this position 1, 166, 236. Okay, so I think let me see if I can easily find it out by my eyes. So sometime it is tricky to find by eyes, but anyway, I have given you 3, 4. Is one of them is missing actually. Can you guess where it is? Can you see? CHR.
Sir, lower right corner.
lower right corner. Second row?
No, sir, last. Second last.
Yeah, there is one here. 1, 2, 3, 4, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, right? Yeah, all of them are here now. So now these are at these positions. The start positions are like this, okay? So now what we can do? So we compute the distance from the first occurrence in other four, other things, right? So the distance is what? 166 minus 1 is 165, right? 235, 275, and 285. These are the distances, right? So we can compute the GCD of all of them. It turns out that GCD is 5. So very likely that M is 5. Very likely. Okay. So by looking at this, we can guess that M is 5. Now we want to confirm that M is 5. So what we do? We compute the probabilities. Okay. So we compute the probabilities. I think I am not doing the calculations, but writing the probabilities for M is equal to 1. Suppose M is equal to 1, then IC turns out to be 0.045. Okay, in the substrings method. If M is equal to 2, index of coincidence turns out to be 0.046 and 041. M is equal to 3, IC turns out to be 043, 050, 0.47. Okay, M is equal to 4, IC turns out to be 0.42, 0.039, 0.045, and 0.40. Okay, for M is equal to 5, IC is equivalent to 0.063. So now you can see that it is in the same range, 0.068, as you would expect. 069, 061, and 072. So this is in the same range as you would expect. So certainly M is equal to 5. Okay, from this test. So you need to compute this index of coincidences from the ciphertext. Of course, you can write down the programs for doing all these things. So now, by this, by this time, now you know that how to find M. Okay. So the question is how to find key. K is equal to K1, K2, Km. So remember, to find M, first we guess M by computing the distances, right? And once then we we compute the index of coincidences to find out what is M. Just confirm that M is thing. Okay, what is 5? So here, for example, M is 5, right? Now we will do some more calculations of probabilities to guess the key. Okay, so let me, I think I will require more space again. Okay, so how to find key? So what we do now, for 1 less than equal to I less than equal to M, let F0, F25, F0, F1 up to F25 knows the frequencies of alphabet A, B up to Z in the string yi bar. Okay, in the substrings, right? Also let n prime is equal to n by m. So this denotes the length of yi, length of the string yi, right? So then the probability distribution of the 26 letters in yi. So the probability distribution of 26 letters in yi will be F0 divided by n prime, F1 divided by n prime, F25 divided by n prime, right? Now remember, YIs are the ciphertext substrings, right? So these substrings is obtained by shift encryption of a subset of plain text elements using a shift ki. Okay, using a shift ki. So therefore, shifted probability distribution is Fki by n and F25 plus ki by n prime. Sorry, n prime. Okay. All these subscripts are modulo 26. Now this would be close to the ideal probability distribution of Pu0 up to P25 in the Piper table, you know. Table 2.1, the structural properties of English. Now suppose 0 is less than or equal to G is less than 25, and we define this quantity mg is equal to summation pi fi plus g, I is equal to 0 to 25 divided by n prime. I am defining this quantity mg. Okay, if g is equal to ki, mg is equivalent to summation pi square. You can just check these calculations, which is same thing as 0.065, right? The ideal probability. This is the case of index of coincidence. Okay, if g is not equal to ki, mg will be smaller than 0.65. Okay, so now what we do, we actually, in our example, since k is equal to, since m is equal to 5, right? In our example that we were doing, actually, right? So we can compute mg for 1 less than equal to I less than equal to 5. So now this is a table. This is a table for for I is equal to, this is a value of mg by I, right? Now what we do, we look at the value of mg that is close to 0.065. So this is close to 0.065, close to 0.065, close to 0.065, close to 0.065, close to 0.65, right? So from this we can guess that k is, so these g's determines the shift k1, k2, k5. So k is basically, so you see this is the first row. So this is, you can say 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. This is 9. Then the second one is 0. Third is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. Starting from 0. Then next 4. And then next 19. This is our key. Okay. So this is how we compute the k from the key actually. So once we know the m, then we can compute these probabilities and then we guess the key. So this is all about cryptanalysis of Wagner cipher. I think I will stop here. So I think that's all for cryptanalysis. Hill cipher is a small one. I will give you in the notes. It's a very small thing. It's not very difficult to look at. So that's all for cryptanalysis of classical cryptography. In the next class, I'm going to start Shannon ideas about perfect secrecy and so on. That's very interesting. Again, we'll do a couple of probability things to actually give the foundation of cryptography. This is very, very important. So this was the fun stuff, whatever we have covered. Of course, it involves some technical stuff, but in the cryptanalysis section is interesting. But so in the next class, we'll talk about this one-time pad and perfect secrecy and so on. We'll develop those initial ideas. We'll cover briefly the probability, entropy, those things, some concepts. Okay, and then from there we'll work out these definitions. Okay, so we'll discuss some of those ideas. Thank you very much. I will be posting you the assignment this week, and I hope you can do it. And so I think based on whatever we have covered till now, so this is I am finishing chapter 1 actually of your textbook, uh, by Douglas Stinson. So now we'll be starting chapter 2 next. Thank you. Okay, so